Plus, he never said anything about it on Monday. He never showed up. That's why.
I would like to ask him, but I fear
Wasting my fucking gas. For nothing.
Yeah.
honestly. And not only that, but the time we waited. What we waited like an hour and a half, just sitting here doing nothing. He's not.
No, I think we were only. I think class only passed by like 30 minutes.
Except the one where it was like sine cosine. I got sine cosine. But I understand. But I was definitely
That was
like
my only
hesitant on
class.
putting it in.
Yeah, that day.
That sucks.
And I'm an hour away.
That's good. No, that's
I wouldn't put that on there. I put in the test. I would have not.
literally just wasted your
If I
money.
got sine cosine on the test,
Not only your class money, the class time money, but just also your gas money.
And time, bro. I could have been doing anything else. For the Pearson homeworks, when we redo the Pearson homeworks, we have.
For transferring?
No. For like you know how once you're finished, you can attempt it again.
Yeah.
Is there a way for us to just attempt the single questions that we got wrong?
You should. I allow no order, so you should be able to skip.
Oh yeah.
I don't know. I haven't tried it.
yeah, I would do it. Like everything else is wrong.
Yeah.
The homework's so long. I don't know. Skip around. Yeah, you can skip around. Also, I thought it was like in order. You didn't have to do it at all.
I'm pretty sure it told me that you start the whole fucking homework over again when I clicked
Yeah.
try. So I'm gonna do it and I'm gonna email him.
Yeah.
I would try it, but with a shorter one. If it's like a 40 question, I would do it that one.
Not the 58.
Not the 58, bro. 58 now.
I can see it coming.
Okay, so today we're going to do chapters 5, 6, and 7 again, but I'm going to do problems from your book.
Okay.
And then we'll start chapter 8. So I want to do the problems in order, so we're going to start with chapter 5. I picked 2 problems that I really like. One of these problems will go on your exam. Yeah.
Sorry to interrupt. Like I was just wondering what chapter would be the next exam.
The exam should be on 5, 6, 7, and 8. And all the problems that I will go, one of the problems I go over today will be on the exam. And one of the problems I go over for momentum will be on the exam. And then you'll have a bunch of multiple or like quick short answer kind of things. And I don't know if there'll be a multiple choice portion for this next exam because there's not really anything multiple choice to really ask other than solve this problem. So there might not be that, but there will be a take-home quiz a week before the exam so that you can, it'll be a take-home quiz like the last one, but a lot of the multiple choice questions that I would ask about the questions that I would ask are going to be on there, right? So it's a way to know what's going to come and, Anyways, okay, so let's begin with chapter 5 problems. Okay. I picked ones that I thought were fun. So I believe, depending on your version of the book, this is 5.107. And it's basically you have a loop, and then there's a bead on this loop. So make sure you draw this, okay? Because, the written exam, if you don't have a drawing, it's kind of, you lose points for that. All right. Yeah. What do you mean? Yeah, so it's 3-dimensional. So you're looking in the plane. So this is a 3D. So this is 3D, right? So I've drawn it, right? So we're looking flat at the ring here, but this here is a flat plane, and then this is 90 degrees, obviously, between the plane. Okay, and then this is rotating like this. Okay, so let's draw the forces on this thing, all right? So what direction is my normal force pointing? Is it pointing directly up, to the right, or towards the center? Yeah, so my normal will be this way. My weight will be this way. Okay? But what direction is my radial vector pointing? Is it up, is it to the right, or is it towards to the center? So ARAD, this radial acceleration, is it pointing towards the axis here, or is it pointing towards the center?
The center?
No. It's pointing towards this way. Why? Because remember, ARAD always points toward the center of rotation. And all the examples we've been doing, our rotation has been in plane. So it has always been the center, right? But now we're in 3D, and our rotation isn't around this R, otherwise we'd be rotating out of the plane. We'd be rotating out of the plane like this, for that to be pointing there. Instead, we're rotating this way around the z-axis, so our radial, that has to point to the right. Okay. So, make some angle beta, and then this position, this R, magnitude, is roughly, actually I'm not going to write it here, I'll write it here. R magnitude is equal to 0.1 meters, and the mass, or omega here, equal to 4.0 revs per second. Okay, and I think that's all. Oh, I am going to add in my own coordinate here. I'm going to add in a coordinate. So when you do these problems, sometimes you need another description, right? So theta. I'm going to add in a theta there. And the reason why I did this is because it just makes it easier for me to break up this n vector. So this is n, w. It allows me to break up this n vector into different directions a little easier, right? Because I can just say cosine points towards the center here, and then sine points up here. So let's just do that. So let's do the sum of forces in the z direction. We have n, our normal, right? And its sine component points up, so n sine theta minus w. And this b, while it spins around, this b doesn't move, it just stays at the same height. So is there any acceleration in z?
No.
Yeah, 0. It just stays there. The net forces are 0. Alright, now we need to look at the other region, which is
that the weight or the speed?
well, this is weight. So if you see it like more squiggly like this, it's the omega. So this is omega. Omega. And if you see sharp edges like a Wario symbol, that's the weight. This is also why they like to put the little arrow on top with this bars. This is why that notation exists, because people would get confused about this W and this. This W is a scalar, right? It's a number. This is also just a number, but it comes from a vector, right? Okay, but we have to look at how it's rotating as well. So let's go to a top view. So top view. So imagine now I'm looking down on top. So this is my X, and this is my Y. And then my B rotates around like this. So that's the drawing there from top view. And, but what is this length? What's L? Is L R?
Yeah. No.
Well, I mean, in 3D, right, it is R. That is our distance from the center, right? But we need to know the distance from the rotation. Not your distance from the center, the distance from your rotation axis. So this L needs to be equal to the magnitude of R. Magnitude of R, right, times, right, so this is R here, this length, and this needs to be sine, so it's sine beta. So that's our L, okay? What are our forces here? Well, we have our N vector pointing inward, right, and then our radial pointing like this, and now, the sum of forces in plane. So now I'm looking at in the plane from up top, all the forces that are here. And we have this is equal to, remember it's rotating, so it's V squared all over L, right? And this L will become something. And this is equal to N. Right, but this is the N, the piece of N that's pointing inward, right? So it's N cosine theta, right? And there's no other forces, right? So those are the only forces present in plane.
For the mv squared, the L is only being applied, the division of L is to the velocity, right?
Yeah, so this is the velocity squared, so the rotational velocity.
Okay.
So if you were to draw a tangent line, this would be V. Right? So this V vector is tangent to the circle, that's this V squared. Okay, and our question is, what is beta? So first of all, let's convert everything to beta, right? And let's convert everything to omega. So omega is equal to L V, right? This comes from V equals R omega. Right? Did I get it mixed up? Oh, sorry, so V equals R omega, we use this and we divide by L to get this frequency, right? So if we plug in what we know V to be, this becomes M L omega squared equals N cosine theta. And what is theta equal to? Well, we know that theta plus this 90 degree plus beta should equal this whole triangle, right? So this should be a 180. So this is plus pi over 2 plus beta equals pi. Okay? And from this we have theta equals pi over 2 minus beta. If we plug this in here, we should get this as n equals sine beta. Okay? So now let's put this here. We have m with m L omega squared equals n sine beta. This L here equals the distance, right? Times sine beta omega squared and sine beta. Wait a minute, that's not correct. Hold on, I think I got something flipped around here. I'm missing a cosine beta. Where did I miss my cosine beta? Hold up. this is sine beta, so this should become W divided by cosine beta. So I plug this into here, then I solve for n, and now I'm going to plug in my n down here. Okay? So here I have n equal W over cosine beta. Plugging everything in, our sines cancel, we have m r omega squared equals W cosine beta. Our m's cancel, right? So this is just mg cosine beta. These can cancel out. We solve for cosine, we get cosine beta equals g over r omega squared. And that's the answer. Well, that's basically the answer. If you were to plug this in, beta, and solve for the arctan, beta is roughly 81.1 degrees. So we plug in these values up here. R equals 0.1 meters, right? Revs is, well, we have to convert the revs, right? So do we convert the revs to radians or degrees? I would pick radians. You can do degrees. It depends on what your calculator setting is, right? If you have your calculator setting in degrees, you want to convert it to degrees. So how many degrees are in one revolution? Right, 360. How many radians are in a revolution? 2 pi, right? So that's just, you gotta convert this. Got to convert. Okay.
What do we convert to?
You convert it either to radians or degrees per second. But it's up to you and your calculator. I always use radians in my calculator, so.
Does it matter if we were to begin this with degrees, then right there, at that equation specifically?
Yeah, you gotta convert your original input to degrees.
Alright, and at that point, we just plug it in and all the reasons.
Yeah, it should, yeah.
So you don't have to convert anything else but that value specifically.
No, because G is in SI units, right? And then R is in SI units. The only thing not in SI units is this. Yeah. Yeah, those two units. Yeah?
That whole thing?
Yeah,
No.
yeah. So I literally just convert this to 8 pi and that's radians per second. Alright, so I just multiply by 2 pi. Yeah, you just multiply. So 1 rev equals 2 pi radians. Okay. So some questions about this. Okay, so some questions about this. When does this break down? Like, when does it become anything?
Let's go.
Well, the only thing that can go to 0 here is omega, right? So when the thing stops rotating, this whole expression breaks down. This thing goes to infinity. It goes out of the domain of cosine beta. It actually goes out of the domain a lot sooner. Because if you think about it, when you take beta, you take the arc cosine of this value. And the arc cosine is basically what input gives me the degree output or something. I always get confused how to say it. But basically, the inverse, the domain mapping, right, for cosine is only from 0 to 2 pi. Or from -1 to 1 is the range, and then 0 to 2 pi is the domain. Okay, so I just multiply by 2 pi. And once you start pushing it out of the domain for what it can have, this no longer becomes valid. It's like trying to say what degree gives me an infinite angle. You know? It's kind of, it basically is an invalid answer. Okay. Yeah, it goes out of domain for our cosines. Alright, so that was chapter 5. Let me think for a moment.
I shouldn't put in the answer sheets. This whole thing. I'll just all the examples and the answer sheet. I'll copy all this down, answer sheet, and if I see it, I'll just.
I want to do like those different color things, right? If I were a certain class, I could see more different, more stuff.
Like, I
It's
don't.
not basically
Teach
model
you.
of your book. The only thing that I have is
He just said his answer
the
is 80
examples
degrees.
in
I
my
didn't know we were
background.
looking for an angle.
I didn't know we were looking for an angle.
Like, something
That's why I
happened.
kind of talk about the surfaces.
I'm sure something happened, you know, and then we just got an angle. Like, I don't understand what he meant by this thing. Just tell him I do not understand. Is this spinning?
No,
Or is
after
this spinning?
the textbook,
Or is it spinning like that?
This is a pole, right?
but
And this is being spun around.
some of the examples
But it's like
that I
spinning
do
like
after that, for example, I usually state you won't have to know that.
But why isn't it a circle?
And I start going on.
Shouldn't the circle be like
Okay,
this?
so let's do 5.9.
It's way bigger. It's too perfect. You wouldn't get it.
So this one is kind of interesting too. You have a block, it's getting full. You have another block. A block on this block. And the question is, so we just draw this all out first. So you can see,
I don't know if the drawing is bigger now. Last time it was too small.
A. This surface here is frictionless. And you have your weight here. You also have a normal force here, so you have V, WB, MA, WA. Those are all your forces, but there is friction between blocks A and B. Between A and B, mu S equals 0.75. So there's static friction between these two blocks, and then MA is equal to 8 kilograms, MB is equal to 5 kilograms. And the question is, what is MC such that MA and MB travel together? In other words, you don't have a huge enough mass such that the thing just rips block A out from under block B, right? You know, have you ever seen those waiters who rip the tablecloths from underneath the silverware and dishware and stuff? Same concept. We want to find the speed. Well, not same concept. The actual opposite. We want to find the speed such that everything travels together. We're not trying to rip everything from beneath.
Well, what's the friction between A and B? What's the friction between A and B?
So, first things
Side?
first
I'll
is
put
write
it
down all the body values, right? So, MA, oh, I forgot something. So, if I'm exerting friction between these two surfaces, right, and this block wants to move this way, what's the tendency of block B? Is it to stay still or to move?
To move in opposite
Well,
direction.
it's block, okay, so the blocks are moving, right? And then you start pulling on block A, is the tendency for block B to move or stay still?
Stay still.
Just like
Is this in real time to like the surface?
No, this is Newton's first law. What is Newton's
If
first
it
law
stays
state?
on rest, if it's on rest, it will stay on rest.
An object at rest will stay at rest, object in motion will stay in motion. So this block does not want to move, right?
Speaking as a concept of objects or working with one-ish. The only reason that
they're not merged together. It's one on top of the other. I see what he's saying.
Well, I mean, you have to think of it like the tablecloth example I just brought up, right? How fast are you driving the tablecloth such that the top block?
Well, shouldn't we be finding not the speed? Oh, just never mind.
So-
I'm just,
The weight of MC.
So yes, this
What
block
about the
does not want to
acceleration?
move, it wants to stay here, right? So now, if this block wants to stay here, and the bottom block wants to move, what direction is the top block moving relative to the bottom block? Yeah, to
we
the
just
left.
let the blocks
And
not
if it's
move.
moving to the left, what direction is my friction force?
To the right.
Yeah, to the
It's.
right.
I think
So-
it's technically just being like if
friction
block
is pointing
B
this way.
was just a table with friction,
And this
then
is
block A was
4B,
just.
I get it. I just don't know. I don't get it.
4B, right?
I think
So my block A exerts a force on B, right? But now my block B needs to exert a force on block A, right? So we have another one coming this way. This is on A. Okay? So you have these two friction forces happening that are equal and opposite between these blocks. Okay. So let's write out the forces on block A. So this would be the tension. So I've got to label that tension. So you have the tension minus the friction force, right? Because it's pointing this way on this block is equal to the mass of the block times its acceleration of block A. And we also have this normal force that cancels out with this, basically NA equal to WA. Okay? Then we have MB. Now the forces on MB are just basically the only one, friction force, right? And then you have the weights. So you have Fs equals MB times AB. And then again, MB is equal to WB. And the only reason for that is because it's perfectly flat, it doesn't seem clear, so the normal has to be equal.
Yeah, not great. Static friction.
Okay? And then lastly, we have MC, where it's minus C plus WC equals MCA. I took this minus because it's assumed to be moving down,
Reasonably
and I
enough.
multiplied it through, so that's why this is
For the forces, right?
Just
Alright.
find the limit or static.
And
Static.
I believe,
Static has to be.
and lastly,
Static.
Yeah, we have to find the limit, and we have to find
We
something
want-
but also move.
The speed enough so the static friction is not overcome by the speed of block A.
to move together.
Maybe we try to find a minimum here.
Trying to beat you back.
So, AA has to equal AB has to equal AC. Okay, so let's start with equation, let me label these. This is equation 1, equation 2, equation 3. Equation 2 gives mu s mb g is equal to mb ab, which I'm just going to write these as a now. So this is just MBA. And your mass divides out, and so this just gives A equals mu SG. Right? Again, our job isn't trying to find the acceleration, our job is trying to find the mass that MC needs to have, right? So let's add equations 1 and 2. So we're adding,
Wait, where do you get the new PG? This is what's second or thing? So yeah.
So we look here, 1 plus 3, these t's cancel, you get a minus fs, a plus wc, and then these two added together. So we have minus fs plus wc equals ma a plus mca. And plugging everything in, we get mu s m b g plus m c g equal to m a mu s g plus m c mu s g. So I took this here and plugged it in for these.
He plugged in both. So
Now we need
he
to
got
put
A
the
along
like
with the other
terms.
one.
So what I'm going to do here is basically solve for an MC. I want to move my MC over and move this over and get everything all on one side. And when we do this, we have mu s mb g equals ma mu sg plus mc mu bg minus mc mu sg. Alright, and then I'm just trying to solve for this m here. So I'm going to move, oh yeah, this be negative. So this mu s mb,
Just U S is where you need to.
where?
The UP needs to MC.
Yes.
Where does that go to?
Hold up. Oh wait, no, not here. This is just this. This is this term moved over here. So there's no mu.
Well, you label it as mu b.
Oh, sorry. Yeah, we can do that.
Okay.
Okay.
Cool.
So we're left with mu s mbg equals ma mu sg plus mu s minus 1 mcg. So I just factored out this mcg, and then I get a minus 1 here, and then mu s here, and this is this one. If I solve for everything, I have mc equals minus mu s mb g minus ma mu s g all divided by mu s minus 1g. So basically what I did here was I subtracted this over, right? So mu s mb g minus
No, that makes sense.
ma mu s g. And then I divide by mu
It's
s
going on
minus
straight
1 here. And then, oh yeah, we still have the g here. And I divided by mu s minus 1 g. Okay. And you plug everything in, this gives you 39. So we plug everything in from up here. Mu s equals 0.75, ma equals 8 kilograms, and u equals 5 kilograms. Right?
I just have to remember.
We plug that all into here, and we get 39. Not standard.
Thank you.
Yeah.
It is simple because you just can't go out and like.
I might ask this question on the exam and does add friction here.
Okay, move this to the other side. Expand. Isolate.
Yeah.
said he's gonna add friction here.
Yeah.
Yeah, he'll be good.
We do it through
Honestly,
the
it doesn't
friction,
change
right?
much.
So,
It doesn't,
because the
but-
friction is proportional to that
He
end.
said he might.
right? And
He
that's
doesn't
the
say
way
he doesn't
That's
say
a
he
will.
N equals, right? So,
That's a
N
will,
equals
if I've ever
that
heard it.
way. That way it affects the,
What's going on? So bad, guys. That would make sense.
That's what makes sense. I like it. I just have to remember to add 1 and 3, which I won't remember, which means
Okay.
I killed the exam. But it's not.
So that was chapter 5. Those are the two chapters, those are the two problems I would probably pick from for chapter 5. Or at least something in those lines. So let's see. Chapter 6.
My brain was eating this. What is this? 6.67, right? Yeah.
So you have a box flying to the right here,
1 second.
and its speed
I'll find it anyways.
is 4.5 meters per second.
Okay.
4.5 meters per second in the x-hat direction. And the mass of the box is equal to, watch, I don't think it matters. No, it doesn't matter. But we have a region here where mu k is equal to 0. And at some point it hits a value where mu k now equals 0.1. And then it goes some distance, and then mu k linearly increases to 0.6 and travels a distance of 12.5 meters, or, well, it doesn't travel, but that's the distance that this thing happens. And the question is, how far does the box slide before stopping? So this is purely just work energy theorem, right? So what is my total
That's
energy
just
of the system?
it's linear increasing from 0 to 0.6, right?
Is the total energy of my system kinetic, potential?
Kinetic.
Yeah, it's purely kinetic, right? And what are the sources taking the energy for my system?
Friction.
Friction, right? So the total work of friction on my system needs to be equal to the total kinetic energy of my box, right? That's the only way that it can stop, right? Is if it absorbs all that energy. So the change in kinetic energy needs to be equal to the work done by friction. What is the work done by friction? It is the work of friction plotted with the displacement, right? This is equal to minus mu k and delta x, right?
That's distance.
So in that case, we're talking about the UK graphic.
What's delta S? Or just what?
Yeah, linearly,
Change
so
of
we're going to
distance.
talk about that. What is mu k?
1.8.
No,
Coefficient
this
of
is the
kinetic friction.
coefficient for the kinetic
Oh,
friction.
it starts increasing now.
So what is mu k? What is the equation for that?
Kinetic friction.
Well, linearly increases from 0.1 to 0.06, right?
The normal
So you need to actually use that old math equation, y equals mx plus b. Right, so you need to know, you need to figure out the slope. So the slope from here to here, what is that? It's 0.6 minus 0.1 divided by 12.5, right? So that's the slope along here. And then we are moving in x right? And then what is our initial position B? Well, let's just make this 0, right? So if we make that 0, then, oh, sorry, that's not our initial position. That's our initial value, right? So our initial value when x is 0 should be 0.01, right? So that must mean our b must be 0.1. Okay? Did anyone not follow that? Okay. So what I did was basically I created a rate. I said at some endpoint I have mu k final. At some beginning point I have mu k initial. Now I need to create a slope. I need to create a rate with how much this mu k changes with my position. So then I just divided by the distance here. And so that was basically me finding my mu k change per distance. Okay? And I'm only allowed to do this because I said the thing increases linearly. If I didn't say that, I wouldn't be able to use this. If I said it increases quadratically, it would be like this. Right? That would be quadratic increase. This is linear increase, right? There you can also have exponential increase. Right? So there's different functions you could be asked about. Yeah. Yeah. The book tells you. This is the problem in your book, and they tell you it increases linear, but they do not give you this, right? You actually kind of have to use your own thinking about how you formulate the problem. Yeah.
Well, I just wanted to know why you added on the point 0.1 at the end.
Oh, because at 0, right, at position 0, mu k needs to be equal to 0.1.
Just kinetic is
right? So if this is 0, then this b needs to be equal to 0.1.
Okay.
Oh, and yeah,
it's just that this is it is in
this
the
is
plot.
Then we can find
m times
the
the
coefficient.
Yeah, for each part.
exponential.
If I did 0,
I guess
All
now
right, so now that we have mu k, we
that's
can plug this in.
I guess now we would
We
integrate
have delta
from
f,
0 to
we need it.
or delta omega
because then you
f
get the
equals
total change in friction.
and this is actually 0.04x plus 1 times mg delta x. Since x is changing, we need to take this delta x to be very small, and we have to integrate it. So this needs to become an integral.
Right.
We have w equals the integral of dwf, which is equal to the integral of 0.04x plus 1 mg dx. So I converted it to an integral.
Shouldn't it be 0.1?
And now, we want to find this integral for some initial position, some final position.
Sir.
So doing this, we get the change in work is equal to mg minus 0.x squared plus 0.1 xf minus v squared over 2b. Putting this in, we have xf equals minus 0.1 plus or minus square root 0.1 squared minus 4 times 0.02 times v squared over 2g negative divided by 2 times 0.02. Plugging this in, we get xf equals 5.11 meters. There's the negative option, but that's negative, so you don't. Yeah. Let me see.
Because he divided by.
Where are we?
You need the G. Yeah.
Yeah, because we divided by g here
Yeah.
on both sides, so we have v squared and 2g. And let's just check for units. Let's see. So v squared is what? meter squared per second squared. The seconds divide out, you have meters left, and then this has meters, so you have meters squared. So yeah, over time, meters. Okay. A string, and we compress it with a box. And the question is, what is mu k? So this thing gets compressed with delta x. And then it gets let loose and it travels some distance. It stops this distance, so let's call this delta L, right? So it travels a total distance of delta x plus delta L, which is equal to, I believe, 1 meter. And the question is, it travels this distance. We're given also k here. K is equal to 100 newtons per meter. And the mass of the box is 0.5 kilograms. And the question is, what is mu k?
Wait, that's both boxes, right?
So we're
That,
not
it's a
given
single
mu,
box.
right?
It's just how much moved.
I'm going to do this the long way first, and then at the end you will see just how easy we could have taken. We basically could have, we can do the same thing. The total energy in the system. From the spring, right? So total energy is from the spring. Right? So whenever we displaced it by squared, where does all the energy go?
To spring?
To friction, right?
Oh, there's friction. Oh, it's about, okay.
Times the total distance, right? And we're given delta x is equal to 0.2 meters. Right, and there it is. You already have, that's the answer. Right? So this is, all these problems, by the way, are considered challenging problems, right? So they have the double, they have the 2 dots on it, right? So, and they're challenging only because it's very easy to do it a hard way, when you could just look at the concepts and then apply them and then find shortcuts. So by applying this, we can have 1/2 k delta x squared is equal to mu k mg delta x plus delta L. So mu k has to equal k delta x squared divided by 2 mg delta x plus delta L. If you plug everything in, you get a value of 0.41. No, mu s is mu.
What was this like current
Mu k. Sorry, mu k. Sorry, not mu s. Mu k. Right. You want to know what your. This is basically if you want to measure coefficient of kinetic friction, right? You can buy springs that the manufacturer tells you the spring constant of. And then you have your object that you're trying to test against some surface, right? So you make a surface just like this, right? And then you put your object on the spring, you know everything about it, and then you just measure continually, many measurements of how far it travels, and you will get a distribution of mu k. And the distribution of mu k will change. It won't always be 0.41 because it will slide and stop around some average. So really, this mu k is a distribution. It varies experiment. Okay. There was a problem we were dividing by nuclei. Where is that? Here, this problem. So we were dividing by mu s minus 1, and it goes to infinity when mu s equals 1. Does that mean we did something wrong in this problem? Or is there something else about the problem that we don't know? Normally this is an issue, but mu s usually only ranges from 0 to 1. Mostly. It is very, very uncommon that it has any value greater than 1, but it is possible. So those are usually called non-Newtonian fluids, by the way. Alright, so that was that problem. I just did it the easy way. I didn't want to take the time to do it the long way because if you want to do it the long way, it's basically write it all out, right? So the change in kinetic energy is equal to the change in the work of the spring plus the change in the work of friction. When you do it like this, you have to break it up in segments. There's the segment where when it's being truncated, right, and then there's the segment where it's moving, and the work on the spring and the work on friction, you can get what do you call it? They don't show up in the same space. You have to kind of add them together. But that's how you would do it. And then, so that's stage 1. So stage 1 is when you have the work of the spring plus work of friction, right? The next stage you just have delta
G,
K
because it's the to work. So it's gonna be kinetic friction, mg, and then the change.
And then this stage 2.
Yeah.
This is the official force, this is the only force acting on it.
Yeah, exactly.
So that's when it's sliding. That's when it's moving and sliding across. So this is a long way of
it's
doing the
one.
problem. You basically write
He
everything
writes over
out,
there,
you
it's
read
one
what's
on
there,
top.
and then you plate the two, and then that's how you, and then you solve for mu k. That's how you get the answer. The other way is just to say, where is all the energy stored and where is all the energy going? Right?
That's the thing. I don't know what to say. Like, you don't know what's coming next. There's no way. Especially when he writes a roller coaster.
I know.
That's not be taken half page.
Friction doesn't matter.
If you have some roller coaster, it goes
Okay, it's
down,
energy.
up,
I can remember this. This is super easy energy
down,
question.
and up. This total height is 55 meters.
Shouldn't be bad. Too bad
So
actually.
we're gonna park here. This park is point A. This is point B.
Is the music blurry?
And the question is,
I could feel the G-force.
the question is, what is the speed at point B and the force U? I noticed we did the rotation problem back in chapter 5, but it still shows up here in chapter 7. Right? Okay, so it moves along, goes along this track. This height here is 3 meters. And this height here is 12 meters. that they give you are distractions in your book, by the way. Right? Because if you remember when we talked about moving through a gravitational field, right? Also, does my normal vector even matter here for friction? No, right? Because it's frictionless. The only thing that we care about when our normal is when we're inside this loop, where our normal would point down, right? And then our weight would also point down. And we'd be moving at some velocity, VB, right? And here, they tell you you start at roughly 0. So VA is roughly 0. Okay, so if I move through a gravitational field, does that matter how I get there?
No.
No, it doesn't, alright? Because if I move down, I lose the energy, but I gain it back when I move back up, and then I move down, I lose it again, and then I gain it when I move back up. So really, all that matters is the total energy based off this height difference, right? So my potential energy, delta U, is equal to mg times 12 minus 25, right? Or height V minus height A. And then based off our work energy theorem, right, we have delta K is equal to delta W. But if the only thing doing work on you is the gravitational field, then this is equal to minus delta U, right? And delta K we have 1/2 m VB squared minus 1/2 mVA squared equal to minus mg HB minus HA.
It's percentage. Okay. Oh, that's simple.
So I just labeled them HA here, or HB. HB here, HA here. Alright, we started out at roughly 0, right? So this is 0. And then if we can just then solve for BB. So this becomes BB equals 2G HA minus HB squared. So I divide out my m's. My m's divide out. And then I multiply by my 2's here. 2 on both sides. And then that's how you get that.
You just square root everything. You plug in and square root everything.
Plugging everything in, this gives me VB equals square root 2G HA minus HB equals 15.9.
Why do you switch up HA and HB?
Question.
Oh, that was a mistake.
Yeah.
Just to double check, the second part of the formula turns to 0 because the initial velocity is 0.
Yeah. Yeah.
Should it be HB minus HA?
No, you have a negative out front.
Oh, and it can't be negative, yeah.
So I just put it in and then I flipped them.
That makes sense. Einstein today.
Okay. So now we know how
And it makes
fast we're
sense now
moving,
because now it's
right?
positive.
Yeah.
So how much force do we feel? How much force do we feel? Your book words it kind of weird. I don't know how they worded it, but if you read it, it's just basically what they were asking. So we have the total force on us is we're moving in a circle. Remember that. We're moving in a circle, right? This is VB, this is R, and we're pointing,
Upwards.
our radial vector should be pointing down, right?
Oh,
So this is minus.
hey, why?
Our normal is pointing down, our weight
Why
is
was it
pointing
oh, because
down,
we're the top position?
right? So that's all the forces on
This
our
is
body.
perspective, right?
We can add this over and then add this over, right? So I add this to the right side and then I add n to the left side. And get n equals mv squared over r minus w. The mass they give us here, m, is equal to 350 kilograms. Right, so I plug in 350 milligrams or 350 kilograms times this speed squared divided by my radius. What is my radius?
6.
Well, my whole diameter is 12 meters, so the radius would be 6 meters. So r is equal to 6 meters. Right? And I subtract my weight, which is m times g. I plug everything in, which should give me 11438.76 newtons, or in scientific notation, 1.14 times 10 to the 4 newtons. Dividing by my weight, n over w, this gives me 3.3 Gs. Okay?
G-force, yeah.
It's very easy if you didn't remember how it doesn't matter where we are, how we get to point A or point B from point A. If you didn't remember that, you can use conservation of energy at every press,
Yeah.
right? Because you know where your height is, and then you can solve it that way. But that's long and tedious. It'll take you probably about 30, 40 minutes to do it. Then if you know your mistake somewhere, another 10 minutes to fix it. And then, you know.
Alright.
All right, any other questions? I think that's all the problems. So 1 to 2 of those problems will be on your exam. They're in your book, right? But I will make slight changes, like I might add friction to the floor, or I might say, you know, I might just give you a friction value and say find the energy or something, right? So, or I might say, you know, along the path from A to B, the work of friction is equal to 1,000 newtons, right? So if I say the work from A to B is worth 1,000 newtons, right? So I've given you the energy of friction. You need to add it into here, right? So plus work of friction.
Minus.
And then do this whole problem again, and you would find a different answer, right? It would be slower, right?
No, it might be.
You might not even reach the top of the hill, in which case you would write that. There's not enough energy to reach the max height, right? Because look how many we have here. 1,000, yeah, okay, it'll be down to 10,000. Maybe you can do that. So how much energy to make it up to point B?
Is it potential energy plus
From
friction?
the
Yeah,
bottom
from
here,
the friction
point B,
shouldn't be
from here, how much
minus
energy to
friction.
make it up to the top? What's doing work on your system as you make it up to the top? Without friction. No, just in general. So you want to move up to point B, how much energy do you need?
No, plus friction, because friction is like doing, yeah.
How much more potential? Yeah.
MGH. Because the only thing doing
Yeah,
work
it's
on
gonna
your
be
system
potential,
from
yeah,
the
okay.
bottom of this point to the top of
Potential
this
energy
point
was
is
positive,
gravity,
then
right?
friction would be
Yeah, yeah.
So the total
It's still gonna be
hypothetical energy you need to work against is MGH, right? But now, let's say you added friction, right? So now you have to add in, I would have to tell you, right, from, let's call this point C. I would need to tell you from point C to point B, the work of friction is, I don't know, 100 newtons, right? Because if you actually try to evaluate friction along this loop, can you just multiply by the distance of the arc length?
Yeah.
That's a loop-de-loop.
So, no, not really, because our friction direction changes.
Oh,
So friction, the force of friction changes here.
that's true.
It always points against our notion of travel, right? And so when you write out this expression,
There'll be a lot of vectors.
when you write out this expression here for friction along this surface, this is no longer constant because it changes direction.
Yeah,
It's
so now we'll be in
always tangent
vectors.
to your path of travel.
for each
So
angle.
there will be an angle
So
between these
I'm
two,
guessing integrate a polar
right?
coordinate.
There'll be an angle between these two,
Just hope it doesn't
and it'll be fueled by the
It's so much
direction of the
better. I
angle.
think life would be so much better if you did that.
But anyway,
bottom like with this, it should be a polar coordinate.
it will work out that you could multiply
Because
by
yeah, because then it's just polar coordinates with each angle of the
Because
radius.
you do need to integrate over the angle. Alright, so but that's a side note. I won't make you do that. I will just tell you the friction from point C to point D is 100 units, you know. And then you use your work energy theorem to figure it out. Okay, we have some time. Alright, chapter 8.